Good morning and welcome to this Copernicus Marine Service workshop training dedicated to the Baltic Sea. My name is Ergan Fouché. I work at Noveltis as an ocean engineer and I'm going to be your trainer for this session. So this video and this notebook are dedicated to assessing the evolution of the eutrophication of the Baltic Sea. And this notebook works like any other notebook. It has code and text cells. If you want to run a code cell, you can click on the arrow on the top menu, or you can use the keyboard shortcut Shift and Enter. If for any reason the Jupyter Notebook does not work anymore, you can click on the button here on the top menu again, and it should solve your problems. So this notebook, two notebooks have been developed for this training workshop about the Baltic Sea. This notebook is the second one, and the first one was dedicated to beginners, and we learned the fundamentals of Python. We learned how to manipulate and visualize the Copernicus Marine Service products within Python. And this notebook is, it has been designed for intermediate level users, and we're going to address a serious issue about the Baltic Sea, which is its eutrophication. So the eutrophication is a major issue of the Baltic Sea, and it is due to an excessive input of nutrients coming from the land and running off to the sea. These nutrients, they are generally nitrogen and phosphorus, and they come from the excessive use of fertilizers, detergents, fish farming waste, industrial discharge, and sewage. And so when these nutrients coming from the land, when they reach the sea, it creates an excessive supply of organic matter, and this organic matter leads to algae blooms. So it creates a green coat of algae on the sea surface, and this coat prevents the light and the oxygen from reaching the deeper sea layers. So eutrophication is a threat to human life, to human health, and also to marine species, as all the marine wildlife living at the bottom of the sea can't survive eutrophication. So this issue is well known now, and in 1988 the Baltic Marine Environment Protection Commission, which is called HELCOM, agreed to take actions to reduce the nutrient loading into the Baltic Sea. And the aim of this notebook will be to assess the results of these measures and to monitor the evolution of the eutrophication of the Baltic Sea. Before we start our study, we need to initialize Python. We need to initialize the Jupyter Notebook. And so we're going to use these 4 libraries, which are Python libraries. The first one is NumPy. It's a very basic library for computing with Python. We're going to use also the Xarray library, which is the library dedicated to the use of netcdf files in Python. Very useful library. We're going to use Matplotlib for the figures and Cartopy for the maps and geospatial data analysis. For each of these libraries, you have the link to their website, and if you need help with some function, if you have some specific needs, you will probably find everything you need on their documentation. So let's import the libraries and run the following cell. I'm using the keyboard shortcut, so this is why you won't see me clicking on the arrow on the top. In the first notebook, we have seen that there were several ways to access the data, the Copernicus Marine Service products. One of these solutions was to use the OpenDAB service. It enables to stream the product instead of downloading it. So here in this notebook, you will see that each of the data we're using have already been downloaded and they are available in the data folder. But if you want to use the OpenDAB service, you can. In the rest of the notebook, you will have the option. I'm going to show you. But to use the OpenDAB service, it's really easy. You just have to run the following cell, enter your Copernicus Marine Service credentials here, and then you'll be all set to use the OpenDAB. If you're not sure how to use OpenDAB, you can click here and it will open the first notebook in which you have all the explanation on how to use the OpenDAB. So we're going to study the eutrophication of the Black Sea, the Baltic Sea, sorry, thanks to one Copernicus Marine Service product, which is the Baltic Sea Biogeochemistry Reanalysis Model. If you click here on the product page, you will have all the information of the product, of the model. You can see that it has two data sets, one with daily means and another with monthly means. And here we're going to use the monthly means. We're going to take all the time that are available in the model, so from 1993 to 2020. The spatial resolution is 4 kilometers by 4 kilometers. As I've said, we take monthly means, and the vertical coverage of the model goes from 0 meters to minus 700 meters. This is the spatial coverage of the model, so it covers the whole Baltic Sea. If we go back to the product information page, you can see that you have plenty of variables here. The ones we're going to use are the concentration of nitrate, chlorophyll, and oxygen. So the nitrate will be used to represent the input of nutrients into the Baltic Sea. The chlorophyll will be represented will represent the algae blooms, and finally the oxygen will be used to measure the hypoxia. Hypoxia means the oxygen depletion, and so as we've seen just before, when eutrophication happens, the bottom of the sea suffers from oxygen depletion. The oxygen can't reach the deeper layers, and so this is why we're going to use the O2 variable. If you want more information, you can check on the product page on the catalog. You also have the product manual, the product user manual, and quality information document. So plenty of information for you to go further on this model. So we can now begin our study, and we're going to analyze the evolution of the Baltic Sea parameters. As I have said, we're going to study the evolution of the nutrient input thanks to the nitrate concentration, the evolution of the algae blooms thanks to the chlorophyll, and we're going to study the hypoxia. thanks to the oxygen concentration. So, as I have said before, all the products we need are available in the data folder. But as I have also said, you can also use the OpenDAPS service. So here, for example, you just have to comment and uncomment the lines to access either one service or another. So we're going to use two files, two Python variables. In the first one, we will have the nitrate, chlorophyll, and oxygen surface parameters from 1993 to 2020. And in the second one, we will have all the depths from for the O2 concentration, again from 1993 to 2020. So in the first variable, we have only one depth, which is the surface, and in the second one, we have all the depths. As I've said, you can choose the two options. So here, if we try the OpenDAP service, you just have run the cell. You can to check on the variable names and coordinates, etc. You just have to put the name of your Python variable into a code cell and run it, and you will see everything. So here are the coordinates. We can see that we have 336 time dates, plenty of latitude and longitude. You can check on the attributes of the data set. So here you can see that the chlorophyll concentration is under the name CHL. You can check on the units, etc. You can also see the values. For example, if you want to check which dates are represented in our data set, you can click here on this button, and you can see that it goes from January 1993 to December 2020. You can also see that you have one time date for per month, and this is because we are using a monthly mean product. For this notebook, for this video, I'm going to use the files that are already downloaded, but if you're using the OpenDAP service, it should work just the same. Just to check, if we use the files that are in the data folder, you can see that you have the same information. You have one depth, plenty of latitude, longitude, the same date times, etc. The first thing that we're going to analyze is the evolution of these parameters, of these average parameters over the whole Baltic Sea region. So the model is defined over the whole Baltic Sea. So you have for each depth, for each time and each location, you have a value of the concentration of your parameter. And so the first thing we're going to do is to calculate an average over this region. So for each time date, we're going to have one value of the concentration for each month, and we're going to plot the evolution of this average concentration. To calculate this average, we're calculating this average over the longitude and latitude coordinates, and we're using the xarray.mean function, so over latitude and longitude. And if we run it and check on the results of our new variable, you can see that we no longer have the latitude and longitude because we only have one value per time, and that's it. We're now all set to plot the evolution of these parameters. So the following cell will plot the evolution of the parameters. So the first thing to do is to define the characteristics of the plot. In the first line, we define the size of the figure. Then we tell Python that we're going to have 3 subplots. And this last line defines the space between the subplots. The first plot will be dedicated to nitrate. Here we set the title of the subplot. So it's the average surface nitrate concentration. We add the grid, which are the lines that you can see here. On the y-axis, we'll add the label, which is the units of the nitrate concentration. And finally, we can plot so the nitrate concentration on the y-axis, and in the x-axis you have the time. We define the color of the plot and also the width of the line we plot. So this will create the first plot you can see here, and then we reproduce the same with the chlorophyll and the oxygen. So if you run it, you will see that our figure is made. So here on the x-axis you have the time, and you can see the evolution of the parameters. What we can see from this first figure is that the nitrate concentration seems to have decreased over the years from 1993. The chlorophyll seems to have evolved the same way. It seems to have decreased from 1993. Regarding the oxygen concentration, the results are not as obvious, and this is due to the seasonal variation, because we are not only seeing the evolution year by year, but we also see the variation due to the season, because all these parameters vary depending on several other parameters, such as the ice coverage and the temperature. So in summer you have more chlorophyll, for example, than in winters. This is why you have all these variations. And so to avoid these variations, we're going to calculate the yearly average. So for each year, we're going to calculate the average of these concentrations, and therefore we'll be able to see more clearly how these parameters have evolved. To calculate the yearly average, we are going to use the group by method from Xarray. So it works just like this. You use the group by and tell with the option year, and then you calculate the time. So if you run this cell, I'm going to show you. Remember that before we used to have 336 values with monthly values, and if we run the group by function, you can see that we no longer have the time coordinate. It has become year, and so we now have, if you see the year coordinate, you now have one value per year, and you will also have one value of oxygen, nitrate, and chlorophyll concentration per year. This is what we're going to plot. So we're using the same Python script as before, except you can see on the x-axis we're no longer using the time coordinate, but the year coordinate, because it has changed. And so if you run this cell, you will see the evolution, and you can see that these plots are much easier to read than the previous ones. So what we can see here is that the HELCOM measures seems to have been efficient because the nitrate concentration clearly has decreased since 1993. As a result, the chlorophyll concentration has also decreased. However, the surface oxygen concentrations also seems to have decreased, which means that that the effect of these measures on the eutrophication are not immediate, and that the eutrophication of the Baltic Sea is still happening. It seems that the current oxygen concentration, the oxygen concentration seems to have remained stable from the 20s, but it also seems to be decreasing lately. So in this plot we were studying the average surface oxygen concentration, but as we have explained before, the hypoxia threatens mainly the deeper sea layers, because on the surface the surface is not as affected as the bottom regarding oxygen and the eutrophication. And so this is what we're going to address in the next session, the hypoxia in the deeper layers. Here is a statement to conclude this first analysis. Nutrient inputs from land have decreased as a result of regionally reduced nutrient loading, but the effects of these measures have not been detected yet. Although signs of improvement are seen in some areas, effects of past and current nutrient inputs still predominate in the overall status. So this statement has been taken from stateofthebalticsea.helcom.fi. Oops, sorry. So this is a website, and this web page is dedicated to the eutrophication, and you may find it very interesting if you want to learn more on the eutrophication of the Baltic Sea, especially. So we can now dive into the deeper sea layers, and we're going to monitor the hypoxia of the Baltic Sea. So as I've explained before, the hypoxia is the oxygen depletion in the sea. So it mainly concerns the deeper sea layers. And so in this section, we're going to try to provide an assessment of the hypoxia of the Baltic Sea. So just a reminder again that the hypoxia is due to the algae blooms, which prevent the light absorption, and the algae blooms are one of the reasons for the oxygen depletion, because when you don't have light in the deeper sea, then the organisms can't use the photosynthesis and can't provide oxygen into the sea. This is one of the reasons. We'll see the other reason later. So a conventional criterion to assess whether some sea is hypoxic or not is this criteria is 2 milligrams of oxygen per liter at the bottom of the seafloor. Here is another website you can check if you want to learn about the eutrophication. And so in the rest of this section, we're going to use this criterion, and regarding this criterion, try to estimate, to assess the hypoxia of the Baltic Sea. So let's begin. The first thing we're going to do is to convert the units, because we're going to use the O2 variable the one we have defined before, the one that contains the oxygen concentration for all the depths. And so if we check on this variable, we can see that the units of the oxygen concentration are mole per cubic meters, and the criterion we're using is milligram per liter. So the first thing we will need to do is to convert these units. As we have seen in the first notebook, you can manipulate with X-array, you can manipulate the data sets very easily, and you just have to you can divide and multiplicate the data set to convert the units. Just a tips, the oxygen molar mass is 32 grams per mole, so this is how we convert the units. So we run this cell. This operation takes quite some time because the dataset is quite heavy, but it's done now. And especially if you're using the OpenDAP service, this operation may take some time. And so we can now begin our study. The first thing we are going to analyze is how the oxygen concentration is distributed on the water column. So we were going to plot a vertical profile of the oxygen concentration. To do so, we are going to set 4 locations. So here are the coordinates of the points I chose to study, but feel free to change these coordinates if you want to study any other thing. We're also going to select the date. I chose November 2020, but again, you can choose any other date. And then we select the model, so the one we have defined before, our Python variable O2. And we select this variable at each location and for the date we've set. We're using the .cell method from X-array again. We've used it on the first notebook. And we select the method we select is nearest, so we're going to take the nearest date and nearest coordinates to the ones we have set. And the .o2 at the end means that we are selecting the variable O2. So we can run this cell. And then we can plot the vertical profile. So let's run this cell. Again, this may take some time because the data sets are huge. And so here is the results. I'm going to explain to you the how it worked. But here on the top you have the map of the location of the points we have defined. And here you have the evolution of the oxygen concentration over the depth. So at the bottom it's the oxygen concentration, and here on the y-axis it's the depth. So you can see that on the surface, so near the 0 meter depth, the oxygen concentration is at its maximum, and then in the deeper then the oxygen concentration decreases, and at the bottom it's almost 0. On the red line here refers to the hypoxia threshold we have defined before, so 2 milligrams of oxygen per liters. And so the criterion was if the bottom of the sea is below this threshold, then we can say the sea is hypoxic. You can therefore see that the dots in red and in yellow, at the bottom, they are not below the threshold, so these points are not hypoxic. are not located in hypoxic water, whereas the red and blue points at the bottom, the sea is below the threshold, and we can therefore state that the sea is hypoxic in these regions. So let's have a look at how we plot this. We plotted this figure. Just like before, we define the size of the figure. Then we add one subplot. We add the grid. We set the title, which is oxygen concentration. We invert axis because you can see that the y-axis is decreasing in order to have the surface on the top. You set the x label, so milligram per liters, and the y label, depth. The font size option enables to define the size of the text. Then we can plot the profiles. So on the x-axis you have the O2 concentration, and on the y you have the depth. Again, we set the color of the lines. We add the threshold value of 2 milligram per liter, so we're using this function. This is how you define that you don't want a continued line. You defined the color and the label to put on the legend, so Hypoxia Threshold here. And the final lines here enable to display the locations of the points on the minimap. So these are the 4 points, blue, red, green and yellow. And so in this first line you create the minimap and you set the projection you want. You add the grid lines. We remove the latitude and longitude labels on the top and on the right. We add the land mask. We set the extent of the minimap, sorry, and then we plot the location of the 4 points with their color. And finally we add the legend, so the hypoxia threshold we had set before. We add it not to the plot, and this is what it creates. So we began to analyze this figure, but let's see why the oxygen concentration is distributed this way. There are 4 main reasons to this that are listed here. So on the surface, the ocean is almost mixed with the atmosphere, and so on this interface the oxygen can dissolve easily into the ocean. So this is why we have plenty of oxygen on the surface. On the surface water, we also have, even if it's too much algae, you also have plenty of vegetation which use photosynthesis to create oxygen, and this is also how the surface water is enriched with oxygen. In the deeper water, as we have seen, you have no atmospheric exchange because we're too far from the surface, and it's also too far from the surface to have enough light to support photosynthesis. And finally, the last reason is that some part of the oxygen is removed from the deeper water because of the respiration of the organisms that live in the deep water, and also the decomposition of organic material. So during after the algae blooms, the algae dies, sinks to the bottom, and then the decomposition of this dead algae creates consumes oxygen and also creates some noxious elements. So if you want to know more about the sea oxygen concentration and all these phenomena, you can have a look at this this article, very interesting article. So now that we know how the oxygen concentration is distributed on the water column, we're going to try to locate the hypoxic regions, and to do so we will select the minimum values of the oxygen concentration, because as you can see here on these profiles, the bottom oxygen concentration is usually the minimum oxygen concentration. So to select the minimum, we're going to use the X-ray method minimum. So we select the minimum from the depth coordinate. Once again, we're going to operate this function and then see the result. And you can see that we no longer have the depth coordinate, because we only have now the minimum value along this coordinate. But we still have values for each latitude and longitude and time. To locate the hypoxic region, we're going to select one date time. So here we set, for example, August 2020. And we're going to, the aim of the following cell will be to plot in red the locations that are hypoxic, and in green the parts of the sea which are healthy, which do not suffer from eutrophication. So once we have set the date, so here August 2020, we select the model at this date. So again, we use the xarray.cell method, and we use here we select the O2 variable. We select we define the characteristics of the plot, just like we did before. Like we did for the minimap, we define the projection of the map. We add the coastline, the grid lines. We remove the latitude and longitude labels on the top and on the right. We add the land mask, and we set the extent that we want. This is the function we're using to plot the two categories. So here the first variable is the x-axis, so the longitude, then the latitude, and finally the oxygen concentration. And we're going to set three values which refer to the the first and the second refer to the limits of the first category, whereas the second and the third are the limits of the third category. So this is the color map we're using, so it will go from red to green. We add the subtitle of the figure, so the title would be Hypoxia Assessment on Date, the date being the the string you have defined before. Then you add the color bar, and we're going to change the labels of the ticks of the color bar, saying that below 2 milligrams per liter the sea is hypoxic. We put the hypoxia threshold, and then we say that above 2 milligrams per liters the water, the sea, is healthy. And so this is the result. Oops, let's run it. This is the result of our study. So of the cell we just ran. You can see that the green area is where the Baltic Sea is healthy, and the orange area is where the sea is hypoxic. You can just note that here we have studied only some part of the Baltic Sea, but if you want to download some other product with another region, another part of the Baltic Sea, feel free to do it, and you may find also find some interesting things. But because we did not want to download too many files, because the files are already very heavy, we are only studying here a part of the Baltic Sea. We are now going to see how the hypoxia has evolved. And to do so, we're going to calculate, just like we did before, we're going to calculate the yearly average of, the yearly hypoxic area. So the first thing we need to know to do so is that one pixel, one cell of the model, its size is it's the resolution of the model is 4 kilometers by 4 kilometers. So one cell, its area is 16 kilometers square. And so if we count the number of cells that are green, and then or if we count the number of cells that are orange, and then if we multiply this number by 16, we will have the area in kilometers square of Hypoxic Sea. So this is what we're going to do, but we're going to do it with with the yearly average. So we're going to use again the group by method. So this is what this first line does. Just the same as before, we group the file by year, and then we calculate the average over time. Note that here we're going to use the same criterion, like if the minimum of the average is below 2 milligrams per liter, then we will say that the water is hypoxic. But you can also select some other criterion that might be relevant. For example, you could take the median oxygen concentration, etc. Or you could set that if the water has been hypoxic for 2 years or more, 2 months or more, then the water is hypoxic. So there are plenty of criteria. We're going to stick with the basic one, which is that if on average the bottom oxygen concentration was below 2 milligrams per liter, then the pixel will be set hypoxic. I hope this is clear. Anyway, here is how we're going to proceed. We calculate, as I said, the O2 minimum oxygen concentration per year on average. Then we set we initialize the list that we're going to plot. So we're going to have on the x-axis the years, and on the y-axis the area that was hypoxic. And then for each of the years that we have calculated, so from 1993 to 2020, we're going to select the year. So we take the year from the yearly average we've calculated. Then we use the X-array method where and count. So where is used to select only the cells, so the locations where the oxygen concentration is below 2 milligrams per liter. And then we use the function count. This function just counts the number of cells that are that have passed the filter we have applied with the where function. Then we multiply this value per 16, because as we've seen, each pixel has an area of 16 kilometers square. And then this area parameter, Python parameter, will be the area we're looking for. So we add it to the list. We also add the year to the list, and we can now plot the chart, the bar chart we want. So again, we set the size of the figure. We add the one subplot. We set the title, the labels of the axis, and then we use the bar function to plot the bar charts. So here is the results. So for each year, you can find the area that was considered to be hypoxic regarding our criterion. And so we can see that although we have seen before that the HELCOM measures had been efficient on the input of nutrients, etc., we can see that on the region we're studying, the water, the hypoxic water still increase, and so although and even though from 2000, about 2000, the level, the area of hypoxic water remains stable or somehow stable. It is still very high, much higher than in the beginning of the 1990s. And so this is the proof, or one proof, that the eutrophication is still threatening the Baltic Sea. We can also see that the areas concerned by this problem, the condition of the Baltic Sea evolves over the year. One year, some years can be critical, and then the other ones are better. This is one of the conclusions we can make. But the main conclusion is that the eutrophication of the Baltic Sea is still a very serious issue, and it's not completely solved yet. So this is the end of the exercise I wanted to show you today. I hope you enjoyed it. I have prepared several exercises for you to go further with this exercise. So the exercises for beginners are here in the section 3.2. You can change. You can select. We've calculated the average over the whole region, but you can select some part of the Baltic Sea and see if you analyze other evolutions. On this section, we have set the location of 4 points to study the vertical profiles. You can change the location of these points and see if you observe some other values. Here on this section, we have chosen one date. So if you change this date, you will have the hypoxia assessment on another date, and you might, if you want, for example, to see how the area was in 1993, this may be interesting. Oops. So these were exercises for beginners. You have also intermediate level exercises. On section 4.2 here, we have studied the vertical distribution of the oxygen. And if you change the location, as I've suggested before, you may see that some values go below 0, and so these are when there is absolutely no oxygen in the sea, and besides the algae, the dead algae at the bottom create hydrogen sulfide, so then the oxygen concentration becomes negative. So this is called anoxia, and you can try to reproduce the map here. So here we have 2 categories, so healthy and hypoxic, and you can try to add another category with anoxic regions if the oxygen concentration is below 0. This may be interesting to see which part of the Baltic Sea is actually anoxic more than hypoxic. Again, with this map, we have been plotting only one date. On the first notebook, we have seen how to create animations, and so you can try to make a loop on these dates and see how the hypoxic region has evolved. On this chart, we are plotting the hypoxic water area, and the units are kilometer square. But it may be interesting to see to have this chart as a proportion in percent of the Baltic Sea that is concerned with hypoxia, and it may be interesting to see how the proportion has evolved rather than the area has evolved. So these were for intermediate level users, but if you're an expert with the Python and Copernicus Marine products, then you can have a look at the HELCOM website. It has plenty of indicators, such as the chlorophyll, the water clarity, the oxygen, etc. These are the indicators that are used to assess the eutrophication of the Baltic Sea. Here we have used a very basic threshold, which is 2 milligram of oxygen per liter of water. But you can try to have a look at the other indicators. Many of them can be found in the Copernicus Marine Service catalog, so you can try to use them and see if you have the same result as in this study. And finally, so the evolution of the eutrophication does not only depend on the nutrient input. It also depends on other parameters, physical parameters, such as the temperature or the sea ice coverage, as I've explained before. In summer, for example, the production is the algae production is higher than in winter. And so the temperature and the sea ice coverage, for example, they can be found in the Baltic Sea physics reanalysis model. And so you can try to use this model either with OpenDAP or downloading it from the catalog, and you can try to see if you can have some correlation between the eutrophication and the global warming, for example. And finally, if you want to go further, you can have a look at the Ocean State Report. Here you have either the summary or the complete, the full report, and you have plenty of information on the eutrophication and on the Baltic Sea as well. It may be very interesting for you to read this. And you may also be interested in this article, which I have used for to create this exercise. This article uses the Copernicus Marine Service workshop, the Copernicus Marine Service reanalysis product, the same as we have been using here, and this product is also used to assess the hypoxia of the Baltic Sea. So this is the end of this video and of this workshop. I really hope you enjoyed this exercise, and I thank you for your attention. You now have plenty of tools to study the eutrophication. Feel free to reuse as much as you want all the scripts that were proposed in this exercise. And if you need help on this notebook, or if you need more information, or if you want the solution of the exercises, do not hesitate to contact us at the service desk email. And thank you again for watching this video and attending the Baltic Sea training workshop. See you soon. Thank you.